Thank you and good morning. I'm basically a social professor at UBC Fisheries Centre. At least I think it's still called that. We're under restructuring, so the name will change any moment now. So in general, basically, when we want to take into account uncertainty in fisheries modeling and stock assessment, we tend to focus on trying to characterize uncertainty in parameters and models. And so the most common approach to doing that these days is with Bayesian methods. Bayesian estimation, we usually apply some Markov chain approach and come up with the marginal posterior distributions for the different parameters and variables of interest. And it's been noted for a long time that uncertainty in parameters is really important, and usually we can get it risk estimates and basically uncertainty estimates with use of parameter uncertainty. But it's also been noted that perhaps even more important are structural uncertainties, uncertainties in the form of the models, the form of the dynamics of the models that were applied, the components that should be in there, and so on. And so while a lot of people have addressed this, on the ground, we see very ad hoc sort of approaches being taken to account for structural uncertainties. And there's a lot of subjectivity going into that in terms of determining what factors are important, what are not. So there's a lot of expert-driven sort of judgment about what's important to account for in terms of model uncertainty, structural uncertainty. And so I've been working a little bit on this over the last maybe 15 years at least, trying to come up with more formalized approaches to account for structural uncertainty. And so I've been working a bit on this in Canadian fish stock assessments. And one approach that I've been exploring for quite a while is the use of Bayes factors. So that's, like this concept's been around, we just heard a talk on that. Although it seems like the experience there wasn't so, I guess, positive in terms of having a result that's easy to interpret and behaves well. But it may be context dependent, and I think that's probably the case. I have found instances where results are really dependent on the priors and so on, but I found other instances where it's pretty robust. And so quite reassuringly, when I've tried to calculate Bayes factors in stock assessment, where I can do importance sampling, it tends to actually provide quite stable, easy to interpret, very intuitive results. So what is Bayes factor? Basically, weights of correct probability interpretation based on probability theory. Summarize the weight of evidence in support of each structural alternative, each different model. And estimates of risk and uncertainty incorporate both forms of uncertainty, parameter and structural. And there's then a rational basis to indicate how much can be or has been learned about hypotheses of interest. So we often forget about hypotheses when we're doing stock assessment, when actually, in fact, we have a very large number of important hypotheses to address. And this allows you to actively calculate, let's say, what's the probability of the data given the model, what's the probability of the hypothesis given the data. And when the hypotheses are different models, this is really useful. So in Bayes' theorem, usually they say, you can ignore the denominator, it doesn't make any difference at all, forget it. Well, that's not the case when you're talking about Bayes factor and when you're talking about trying to calculate uncertainty different models. The denominator becomes the most important part of the equation, and that's what we try, that's usually what we ignore, but it's actually really difficult to actually calculate, and that's why people tend to ignore it. So just a few words on this. So we have effectively the prior distributions. So if we had just one parameter or two parameters or any number of parameters, we have to have a joint prior density function, and it needs to be effectively a proper prior that integrates to 1. You can't do this unless you have proper priors. Markov chain, you can usually get away with improper priors. And then we have to have the likelihood function or probability of data given the parameters in a given model. So we have to do that integration. And when it's Bayes factor, we would pick a reference model. So we'd pick a model we think is, here's our base case model. and now we have an alternative model. How likely are those? How likely is the data given model 1 versus model 2? So we need to take that ratio. Base factor is the ratio of these integrals, ratio of the probability of data model for model 1 versus 2. So how do you interpret this? So we saw in the talk before log base factor. That's kind of a difficult concept. Here it's like just the relative likelihood. How many more times likely is model 1 versus 2? How likely are the data given model 1 or 2? Like, so if we had base factor of 5, the probability of the data is 5 times more likely for model A than for model B. So that's quite a simple interpretation. And as I mentioned, it's tricky to compute, and I find the most reliable approach to calculating it is with importance sampling, which is much less commonly applied than the Markov chain approach. And it tends to work really well for moderately complicated models, but not really well. It doesn't work, it falls over for really complicated models. I'm not going to go through these steps, but it's a Monte Carlo procedure, and we need to define something called an importance function, which is a distribution that is something like, or as close as possible to the posterior distribution to start with. But it's not like a Markov chain in that we have independent samples coming out of it, whereas the Markov chain is a chain of related samples coming out of your, let's say, sampling distribution. And in the end, we calculate something called an importance weight, and that's basically directly proportional to the likelihood times the prior divided by the density of the importance function. And if we take a million draws, we take the average of those ratios, and that's the summary of that integral, basically probability of data given model. So it's really quite simple concept, but it's rather tricky to implement. And in terms of base factor interpretations, there's literature on this in terms of how you'd make a decision in terms of credibility of models, like two competing models. Basically, in this range, it's nothing to write home about, whereas when you're getting up to 10 to 30, it's strong evidence, 30 to 100, very strong, greater than 100, decisive. So up to here, basically, I wouldn't be rejecting models, but if it's getting over 100, then you could actually really maybe discard a model, or you might mention it, but you may not necessarily take it seriously. So just a simple case study application. So I've applied this to a lot of different assessments. Here's an interesting one that's kind of relevant to the theme of the conference in terms of considering ecosystem issues. So in fish stock assessment, the most common approach is really to ignore ecosystem sort of issues. You might try to consider those in terms of looking at deviates from, let's say, the stock recruit function. But one of the primary assumptions is that the primary source of, chief source of mortality is from fishing. And natural mortality rate of recruited fish is constant over time. You don't necessarily have to hold to those assumptions. You can have time varying natural mortality. And when a stock is depleted, the predominant assumption is that it's due to fishing, and the way to get it to recovery state status is to reduce the fishing mortality rates. So we see depletions and lack of recovery for many fish stocks in Canada, even though fishing mortality rates have declined because of management interventions. So there's a big question mark about why are these stocks not recovering? They should be recovering without when the fishing mortality rates have been taken down to very low levels. And so I think it's quite agreed now. The understanding is that there have been some big ecosystem changes, and one of the big ones is the vast increase in pinnipeds, i.e. seals and sea lions. Seals and sea lions on the west coast, seals on the east coast, gray seals on the east coast. And of course, the main diet of these creatures is fish. And in this analysis, looked at a number of different things. What are the contributions of fishing and pinniped predation on the depletion of BC inside waters yelloweye rockfish? How can we address such questions using stock assessment models and available data? What are the implications of systematic changes in predation for stock recovery plans? And could base factors be useful in evaluating the credibility of different hypotheses on the role of predation? So I don't have any time in this talk because it's so short, time available to talk about the details, so I'll just more look at kind of the results. And And I'll just move on here, but well, what about predation? This is something we don't consider in stock assessment. So why might we consider it here? Well, the fraction of diet composed of rockfishes in seals and sea lions on the west coast that ranges up to 11% depending on species, season, location, etc. And the consumption rates are really high in these creatures. For some of them, up to 20 tons per year eaten. It's like a little fishing boat. Another thing that's relevant is that there had been culling in the past up until the 1960s, and then it was stopped. And since then, in BC waters, virtually all the different species of pinnipeds have increased very dramatically. So in the thousands in the 60s, whereas in 10,000s currently, tens of thousands. And the total consumption, like in the waters next to Vancouver, basically had been around 7,000 tons per year. If you look at the bioenergetic requirements and the number of animals, 7,000 tons per year. And then up to about the 1960s, and that's increased to approximately 70,000 tons per year. So there used to be a commercial fishery, several commercial fisheries that took a lot of tonnage out of the Strait of Georgia, inside waters near Vancouver, up in the 1960s, 70s. And since then, those fisheries have gone down to pretty small catches, maybe 20 to 40,000 tons. And the pinnipeds are eating and consuming many more tons of fish than the fishing vessels were. So the situation is really flip-flop. Here's a reconstruction of the abundance over, let's say, the last century in terms of harbor seals. They're fairly high, this impact of culling and hunting, and then increasing up to about 60,000 animals recently. Stellar sea lions coming up and increasing exponentially recently, and and this is California sea lions up in around 2,000 animals. In inside waters every year, migrating in. So I just jumped to the stock assessment results so you can see what do things look like if you do an analysis with the pinnipeds included. Of course, you can, including more parameters and more information, you can come up with a good fit, and we can have quite a good fit to the abundance index data. Several different sources, but quite scattered, but they all show a clear picture of decline, and so we can obtain a pretty good fit and fairly tight probability intervals about abundance over time from way back the early part of the century, around 7,000 tons of animals or rockfish coming down to let's say less than 5,000 tons recently, and continuing decline. And if we look at the reconstruction of let's say fishing mortality rates, the blue line with the probability intervals, and increasing in the 70s and 80s, and then coming right down. So fishing mortality rate being well below the, let's say, the maximum rate of increase, long-term average rate of increase of the population. So that's good, but what's not good is if we follow this brown line, this is the sort of best predicted mortality rates, natural mortality rate from pinniped predation, being really quite low, bumping around, and then coming out steadily and increasing over the last decade or so, and well above the maximum rate of increase. So as a population dynamicist, is that concerning? Is that concerning? Well, that basically is an extinction forecast, which I don't quite believe. If we look at other scenarios for the pinniped, if we had everything at the lower bounds for the consumption rates, it would be under that, but it's still more than fishing mortality rate, and it could be well above if we were at the more pessimistic side. Let's move ahead here. So in terms of the total consumption, the red is the catches, total catches. I think the black is the base case predation in terms of animals, or sort of tonnage of yellow wire rockfish consumed, and now it's well above, way over the fishery, whereas it was higher then lower, and basically it's coming down because the abundance is coming down, but the rates are still very high. If we did projections, if we ignored pinnipeds, we do a normal stock assessment, and we considered, well, how are we going to get this population to recover? All we have to do is reduce the quotas, very small tonnages, and it's a long-lived species. It's 17-year age of maturity, very low natural mortality rate, lives to well over 100 years, something like an orange roughy. And you can see that, well, if we had the catch around 15 tons or so, it would decline slightly. Basically, if we had around, let's say, 10 tons, we can get some increases. Whereas if we include the pinniped predation in there, it doesn't matter what catch you have, it's suggesting we're going to have downward trends in abundance. And the only way to get it to turn around is to reduce the pinniped predation. So if we somehow got the pinniped abundance down to lower levels, so we had an 80% reduction in feature in pinniped abundance, then that's the only way to see things turning around. So quite a radical different viewpoint about what's going to happen to the stocks and how to get recovery, whether you consider the predation or not. And what is important is how credible basically are these, is this alternative hypothesis. And so I basically formulated a fairly simple type 1 functional response in terms of predator, number of prey eaten per predator per year and so on, and a maximum cap in terms of the not really palatable things like salmon. They have a lot of spikes and big bony plates, so they're not going to be something, so they're more taken at random. If a sea lion or seal's on the bottom, sees a rockfish, and it's bite size, it's going to try to gulp it down. So I developed these models, and to make the models comparable, like given the data had to be the same between the model runs. The easiest way to do this was if I had a model without predation, I just switch all the switches for predation down to 0, and pretty well had the same inputs. And I could calculate the probability of that model, and then I'd turn the settings up for the predation and find out how credible those alternative runs. So it's something like dealing with parameter uncertainty in the same model, but if I had all the parameter settings for the predators as continuous sort of parameter space, it wouldn't, there'd be no way to get the model to work because it's too complicated of a space to work in. So if I discretize the parameter spaces to treat them as alternative models, then I could actually get the models to run really neatly, efficiently, and I could calculate base factors for those different model settings. Okay, so in terms of base factors, so relative to, let's say, a reference case model which had predation in it, if I switched off like all the different, or turn the knob down on the predation rates, then it's a highly unlikely outcome. You know, 1 in 100,000 or thereabouts, I think, if I'm reading the zeros correctly. Whereas if I increase the amount of predation up to like half the reference case, then the base factor was about 0.5. If I went beyond the base case and increased those settings, then it went up to 7 and then down to 5. So it seems to be quite strong, well, not, let's say, strong support against a model without predation. Basically, that's the main interpretation in terms of how likely are the data relative to the different model settings. So without predation, highly unlikely. So we went beyond this and we included these results in decision analysis. We presented the results in decision table form to the fisheries managers and basically included the base factors on the chief alternative hypotheses in terms of if there's 25% of the reference case or twice the reference case, what are the outcomes under different projections, and things really don't look too good as you go towards more predation. And so things actually would increase if you happen to have basically a smaller amount of predation, but under reference case and more, we could see from those projections things not looking good. So just to conclude here, results generally cast doubt on stock assessments that ignore variation in sources of natural mortality. When you don't see stock recovery and there's no fishing mortality rates, what's going on there? It's likely natural mortality is increasing. So if you look around and see things like, well, pinniped abundance is increased by a factor of 30 to 50 times, then is that enough to make a difference? Well, from the base factor analysis, it's credible that the natural mortality rate for this species of interest has shown large systematic trends, and from predation it has exceeded fishing mortality rates recently. Both of these sources of mortality have been causes of stock depletion, and quite surprisingly it takes really small fractions of yellowfin rockfish in the diet to make an impact. So as low as 0.3% of the diet being rockfish is enough to make a big impact on the species, because it's one of the lower resilient species in the system. And so it becomes credible from the analysis that lowering allowable catch is unlikely to promote stock recovery, prevent further stock depletion. even if pinnipeds stayed at current levels with no reduction in F, it's not going to reduce. We'll see basically no change. We'll see continued decline. And it's only with a substantial reduction in seal sea lions with no reduction in F that we could see a reverse. But there's a caveat, and that this is just currently a one-sided analysis. I'm only looking at the one source, potential source of, let's say, natural mortality rate. Other things have happened. So, for example, in these waters, key food sources like krill, euphausids, there appears to have been a collapse in that. That's a key rockfish food. So some further analysis, I'll be actually looking at these competing hypotheses, this competing hypothesis, and other things. And just a few words on a few other assessments. So I've looked at link odds, technological creep, base factor showed quite funny things. If I did an AIC analysis, I had completely the opposite hypothesis being supported compared to the base factor analysis. AIC being looking at just the very best parameter estimates, when I account for uncertainty in parameters with the base factor, the base factor supported entirely the opposite hypothesis in terms of technological creep. And I'm not going to go through these, I'm running out of time. And basically, I think I'll skip on to the next slide. So just in conclusion, base factor should not plan, but play an important role in scientific learning regarding different hypotheses and models, and decision analysis when there's uncertainty over different models for how the system behaves. So with that, I'll finish off here. So thanks.